So given these 5 tests to determine whether or not a series converges, what was test number 6?
Was it the direct comparison test?
It certainly is. Okay, and so then that's easy now to know what the next one is. That's the limit comparison test. And then next one, number 8.
The alternating series test.
And then number 9. And number 10. This was the test for absolute convergence, or the absolute convergence test. And then we had the conditional convergence test. Okay, so this here, we can now extend this because we need to put some more tests in here. So we need the direct comparison test. We need the limit comparison test. We need the alternating series test. We need the absolute convergence test. And we also need, let's see, I got 3 more to get in here. Okay, so I need the conditional convergence test. Why are you red? And there are 2 more. And we'll get to those today. Okay, so for the alternating series test, I do want to give you the estimation theorem, the alternating series estimation theorem. And then we'll be on to our next test, which are the last 2, and they are the most fun. Okay, so we want to do the alternating, so the theorem is the alternating series estimation theorem. Okay. And so the alternating series estimation theorem says, consider a convergent alternating series that means it satisfies the 3 conditions of the form summation n equals 1 to infinity of -1 to the n plus 1 times un. Then for n greater than or equal to some capital number n, the nth partial sum, which is going to be u1 minus u2 plus u3 minus u4 plus dot, 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 all the way up to un, which is -1 to the n plus 1 un. So that's the nth partial sum, approximates the sum of the series. The sum we want to call the sum L. Actually, the sum S. This sum S of the series with an error that is less than the absolute value of the n plus first term. Okay. So say I have this series. When we looked at this series, so this series is the summation n equals 1 to infinity of -1 to the n plus 1 over 2 to the n. Okay. So this is 1 minus a half plus a third minus a fourth plus dot, 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 plus -1 to the n plus 1 over 2 to the n plus dot, dot, dot. Now, I don't know what the sum of that series is. I have no idea. But let's say I take 9 terms. So if I take 9 terms, and where did I get 9 from? I just pulled it out of my head. Okay, so if we compute S9, so let's see what S9 is. So S9 is going to be 1 minus a half plus a third minus a fourth plus a fifth. Oh, wait a minute. No, I'm doing the wrong one. I need 1 over 2 to the n. Okay, so 1 over, so this next one will be 1/2 plus a fourth minus an eighth plus a 16th minus 1 over 32 plus 1 over 64 minus, that's not a 64, minus 1 over 128 plus 1 over 256. Okay. I think it's 1 minus a half plus a fourth minus 8. 2, 4, 8, 16, 32, 64, 128. Okay, all right. And so then let's compute S10. So S10, we want the absolute value of S10. So the absolute value of S10, well, let's look at S10 first. So S10 is going to be 1/512. Okay, so that's what S10 is. Why do I feel like that's not? This is 1, 2, 3, 4, 5, 6, 7, 8, 9. That's right. Okay, 1, 2, 3, yeah. So S10 is 0.02. Okay, so it's actually negative that. It's negative. Okay, so that's what S10 is. All right. Oh, come on. Thank you. All right, so the error is less than the absolute value of S10, which is equal to 0.002. So that means that the true value of the true value minus the estimated value that's the error, is less than 0.002. So the true value, which we don't know, so the true value is S minus S9 is less than or equal less than 0.002. So that says S minus S9 is less than 0.002 and is greater than negative 0.002. So S is less than S9 plus 0.002 and it's bigger than S9 minus 0.002. And I forget what S9 was, 0.668. So the true value is less than 0.668 plus 0.002. And over here, I get 0.668 minus 0.002. So the true value of the series, and I truly believe this is supposed to be less, it should be less than, not less than or equal to, is between, so if I add 0.2 to that, I'm going to get 0.670. And over here, I get 0.666. Okay, so I know the series is the true sum of the series is somewhere in that bracket. Okay. The true sum of the series is inside that bracket. Now, how do you find the true sum of the series? So what is the series? So the series now, remember, was sum n equal 1 to infinity of -1 to the n minus 1 over 2 to the n. So factor out sum n equals 1 to infinity, factor out the 1/2, and then I get -1 to the n minus 1 over 2 to the n minus 1. So now this looks like the sum n equals 1 to infinity of 1/2 times minus 1/2 to the n minus 1. What kind of series is that now? What kind of series? I just made it look like the perfect form. You need to know this. Which series is that? It's one of these. It's number 1. It is a geometric series. Remember, the geometric series looks like the sum n equals 1 to infinity of AR to the n minus 1 is equal to A over 1 minus R, provided the absolute value of R is less than 1. And in this case, A is 1/2 and R is -1/2. So therefore, I get the sum n equal 1 to infinity of 1/2 times minus 1/2 to the n minus 1 is going to equal 1/2 divided by 1 minus a -1/2. So I get 1/2 divided by 3/2. And I feel like I did something wrong. Because that gives me 1/3. So I did something wrong. What did I do wrong? I'm off by 2. How am I off by 2? Let me see what I did. I had the summation of -1 to the n. Aha, I know why I'm off. Because this series is not that series. This is wrong. This series starts with n equals 1. So this series, I know what I did wrong. I should have made, first off, that was n plus 1. Oh my God, how have I screwed this problem up? Okay, let me fix this. Okay, so first off, we're going to fix this. This is going to be n minus 1, because that's what I want it to look like. Okay, and it's stuck. Okay, so now we fixed it. So we went back and fixed it to make sure that the series actually matched what we were solving. So in order for it to actually equal what's on the right-hand side, it has to be -1 to the n all over 2 to the n minus 1. Now that matches the series. Okay. All right, so that is good. And I am going to stop this.